Okay, hello again, everyone. It's a day later in my time, but hopefully you're watching this shortly after you watched the previous video on linear regression, because I just want to wrap up what I had to say for the third part of the linear regression discussion. And then, as I mentioned last time, next time we'll move on into ANOVA, or analysis of variance. But where we left off was actually this part where we talked about the connection between the two. And for this last bit, I want to talk about something different, which incidentally is going to help you with your homeworks as well, homework number 8. But if you remember, a long time ago, we came up with a method called QQ plots for graphically investigating whether or not a distribution was normal. And this gave us a way to just kind of eyeball whether we thought a distribution was normal or not. I mean, there's kind of two different ways to eyeball it. There's one way, which is to draw the histogram, and then there's another way, which is to draw a QQ plot. But in both cases, we're kind of just taking a look at it and saying, yeah, it's kind of normal, that sort of thing, right? Or maybe it's not. So I want to give you another way to sort of quantify how normal a distribution is, and it's going to involve what we've been talking about with linear regression and correlations between variables. So let's start, excuse me, by taking a trip down memory lane, for me at least, and loading in the F0 database from the 2013 version of this class. And I'm doing this because these students are at this point long gone, and also because I know what their F0 distributions look like. So we're going to load this database into R with this command. And back 8 years ago, I had people reading the rainbow passage. And if you've done any sort of linguistics or phonetics research, you are familiar with the rainbow passage. And what I did was just extract their F0 values out of that. But yeah, it's some sort of competition. The rainbow passage about some sort of competition between the rainbow and the sun or something. I can't remember. But a lot of people have their participants read that passage as a sample of their speech. And in the case of this particular example, I just wanted to get F0 data from the speakers in the class from what they read. So two of these people were Joey Windsor and Saskia Lorek. And I want to look at their F0 data to see how normal they might be. Not the people, but their F0 data. I already know how normal they are as people, but that's besides the point. So when we were just getting started, as I mentioned before, we visually evaluated how normal a distribution was by making a QQ plot, and this is the technique we used. So you use this QQ norm command. Maybe I'll put this up here, and I'll put the PowerPoint a little bit lower. QQ norm plots gives you this sort of plot of the data. And again, if the data were normally distributed, you'd expect this to fall on a straight line, kind of rising from the lower left to the upper right corner. And then you can draw the best fit line on top of that with the QQ line command as well. And you can see, or actually this is supposed to be what the normal distribution looks like, is a straight line. It's not necessarily the best fit line, but it's not a straight line. I mean, that's totally obvious with this data, and you can maybe see why I picked it. In fact, since I mentioned the technique a second ago, we can take a look at the histogram for Joey's data, and you can see why it's not normal, right? There's a whole bunch of observations down here at the low end of the scale, and then there's, for some reason, a fair chunk of like very high observations between 500 and 600 hertz. And I think actually the reason why this is happening is because I had people read this passage, like a whole paragraph long of speech, and I didn't like count their F0s, go through the whole thing by hand or anything like that. I just had prot script extract the F0 measures for me. And in a lot of cases, I think the prot script was simply making mistakes, maybe because of creaky voice or something like that. It was misreading the F0s, and so it was counting a lot of very high F0 measures for Joey, who's a male speaker and who we'd expect his F0 to be closer to the bottom end of the range, generally speaking. So he doesn't have a normally distributed F0. I hope it's not poking too much fun at Joey to say he's not that normal of a guy, and I think he can handle that, but he's also a very good guy. So I want to just shout out to Joey. Thank you for letting me use your data for this example, because hopefully it's going to be helpful for everybody. So one of the ways that Joey is not all that normal is that he always comes to my board game party. So thanks for keeping on coming to the board game parties, Joey, and don't let this deter you from doing that, because It's hard to find such people. Anyways, how unnormal is Joey's data? So, yeah, it doesn't look very normal there, but you can't we don't know a way to put a number on it, right? We're just saying, oh, that's not even close. We could compare it, I guess, to Zaskia's data. Ms. Lorick, who is now known as Ms. Scrimshaw, she got married, and that's what it looks like. So you can tell this is not also very normal looking because that's supposed to be on a straight line. And if we plot that QQ line, you can see it's not totally lining up with the expectations there. But it looks a little bit better than Joey's did. So is there a way we can quantify this? In fact, there's a long stretch here where it looks like Zaskia's data is lining up with where we'd expect it to be. And so when you look at it in the histogram mode, it's like, yeah, this is, depending on how you kind of divvy up the bins here, this could be kind of normal. But there's a long tail over here on the right, and there's some stuff over here on the left as well. So yeah, it's not normal, but what else is it? So what we can do is we can extract the theoretical normal quantile values for each data set like this, which is basically the expectations of where we think these data points would be if this actually was a normal distribution. We'll do it for both Joey and Zaskia, or Mr. Windsor and Ms. Lorick. And then we can calculate the correlation between the observed values and the sort of expected or theoretical quantile values using the correlation command like this. Yeah, so and overlook saying anything there. But this will give us basically a way to quantify this feeling we have of how normal this distribution is. And ideally, if it's a perfectly normal distribution, we should get a value of 1 for this correlation. So in Mr. Windsor's case, it's 0.555, so on and so forth, like a Hollywood phone number. But that's not 1. But the question is, how far away from 1 is that really? We can compare it to Zaskia's, and we get a higher R value there. It's 0.80 something. So that's also it's not 0. It's closer to 1, but we don't know if it's definitely not exactly 1, but is it far enough away from 1 to say that it's not normal? That's kind of the question we're operating with here. There's 2 questions you can think of. So we can go back and do these linear regression analyses like I've shown you in the past couple of lectures, and just say, well, let's take a look at sort of this linear relationship between the expected QQ plot and the one we actually get. And you can see Joey's R number here, his correlation coefficient is 0.55. Based on that, we can estimate what the slope of that plot should be and then actually calculate whether that slope is significantly different from 0, and it is. But the deal here is that there's a huge number of observations in Joey's data set. So there's over 1,400 different degrees of freedom. If we go back to right here where I was, and just count how many observations we get, there's 1466, right? So if you have a really huge N like that, you're generally almost always going to get a significant effect, no matter what you're measuring or what the effect size might be. So it's not super informative to say, well, this is different from 0. There is some sort of connection here that we might be expecting. There's some sort of normality there, but is it really a normal distribution? And to answer that, we want to answer the question of whether or not these R values are significantly different from 1, kind of looking at it the opposite way. So if this is sort of underlyingly a normally distributed set of values at the population level, and we take a sample of 1,400 different observations from it, will that sample set of data look as weirdly not normal as what Joey's data look like? So the way to test that is with what's called the ShapiroWilk test. And there's different ways to test if a distribution is normal or not. And if you do some poking around, you find out pretty quickly that the one that's supposed to be the most powerful or most statistically powerful is the ShapiroWilk test. And this one is super easy to implement in R. So the command is just the Shapiro test. And then you put your data set in parentheses like this. And I'll run it, and it gives you a very simple output. It basically says, oh, here's your data set, and here are the stats that matter. So I was running this the first time. I thought, oh man, Mr. Wilk kind of got, shorted here on the R command because his name isn't even mentioned in it. It's just the Shapiro test. But the W appears here. This doesn't stand for Windsor, I don't think. We'll say it stands for Wilk. And this is the W statistic that you get out of the of running the command. And then it basically says what the p-value of that is. How do we interpret this? I'll go back here to the notes. The null hypothesis for the Shapiro-Wilk test is that the distribution is normal. So if you get a significant effect when running the Shapiro-Wilk normality test, that means that your distribution is not normal, or that means that based on the results of this test, it thinks that the distribution is probably not normal. In this case, it happens because we have a really low W score. We can kind of go back up here. I'm not going to walk you through the specific details of how to calculate this statistic. It's not super complicated, but we don't really need to know it because it actually winds up being pretty close to R squared, that value. So it's kind of based on some of the analysis we've been doing already. But the main point to recognize is that when that p-value is less than 0.05, that means that this distribution is not normal. Or another way to look at it is that that correlation value we got for this is far enough away from 1 for it to not be normal, is one way to look at it. We can look at it for Zoskia's data too, which looked more normal to us, but we see we get a significant result there too, even though we have a bigger W value. So that's also not a normal distribution. However, I'm going to reiterate the same thing I said before, that when you're dealing with data sets this big, you're almost always going to get a significant effect whatever you're testing. And so for that reason, it almost is kind of a meaningless thing to do. So it might be better to run this with a smaller set of data to see what the results look for just a smaller sample where, the outcome is unclear or uncertain in terms of whether we'll get a significant result or not. So I'm going to go back to this monomorphemic monosyllabic words database. And rather than selecting out the first 5 words from the database, I'm going to select the first 20. And I don't know how much we've looked at these guys, but here's our familiar first 5, which we've seen a lot of. There we go. The famous 5, not quite. But then we also have a number of other words like prop, dawn, dog, skirt, spree, so on and so forth. So, some of these are familiar and frequent. Some of them are not, like how often do you use the word sprig? Maybe at Christmas, probably not. How often do you use the word are? Every day, right? Okay, so what we want to know is what the sort of normality situation here is. So I'm kind of giving away the answers to some of these, but I'm going to look at the familiarity data for these guys and also the frequency data. So if we plot the histogram of familiarity, it looks like it could be normal, right? It's not exactly the perfect shape we're looking for because we want to see it looking more symmetric than this is in the middle, but it kind of has that general bell curve shape, right? We could also test it, though, using this Shapiro-Wilk test. And if you didn't catch this when we looked at the slide there briefly, we find out that our p-value is bigger than 0.05. And this W value is actually quite big. So this is, what you'd report in the stats, but this is what you make your inference based on. So this means that this distribution is normally distributed, or at least you can make that inference. You can accept the null hypothesis in this case, that there's nothing here to tell you that it's not normally distributed. And we can compare that to the frequency data from the same group of 20. And we take a look at this and it's like, that's kind of normal. It's got this weird gap here. And this gap is actually the word R, which I mentioned before, because if we go back up here to the frequency data, we see that R is super frequent, much more so than any of the others, and the rest of them are all kind of combined down here. So, is this normal or not? Maybe it's close enough to the other one that we might think that it is, but if we run this Shapiro-Wilk test, we find that we get a p-value of less than 0.05. You'll note here, too, that the W value goes down a bit as well, but this basically means that this distribution is not normally distributed. So you can report that result if you're worried about that or need to test that for whatever reason. And we'll come up with a few reasons why as we go through the next unit on ANOVA. I have this note here as well that the moral of the scientific story, as usual, sorry, it's getting warm, is that you should always quantify things if you can, rather than just relying on your intuitions. Don't be like Luke in the speeder, use your guidance technology, which we call statistics in this case, to help you out, because it can be hard to see some of these patterns. I think we saw this last time when I was talking in the first part of this lecture, where there was we're plotting random samples of X and Y against each other, and there was one case where the R was 0.2, and it looked like it was no correlation at all. It looked like the numbers showed us that something might be going on in there, even though it was hard for us to see. It's good to kind of balance out your intuitions with what you can actually quantify and pin down exactly, because anybody else can do that quantification step just by following the algorithm, whereas not everybody will have necessarily the same intuitions you do about your data. That sort of quantification helps you make a stronger argument in the long run. And that, helps your work become more influential, presumably, if people are doing things the right way. However, I will add a caveat to this, which is that it's also always important to plot your data and take a look at it. And there's a funny example of this, which I just encountered not too long ago, that comes from the statistician Frank Anscombe. And I'm not enough of a statistician to know this guy, but apparently he's famous in the field. And this example of his is famous as well. So one day he just came up with 4 sets of data that look like this. So we got set 1, set 2, set 3, set 4. They have different X and Y values. Or in fact, if you start looking closely at this, you'll notice that sets 1, 2, and 3 all have the exact same X values, but they have different Ys, and then set 4 looks a little bit different on its own. But these are just numbers, right? And so on the basis of these numbers, you can calculate all sorts of statistics, or I guess estimate parameters, that sort of thing. And when you do, you find that for these 4 sets of data, each of them has the same mean for X, the same mean for Y, the same variance of X, the same variance of Y. Also, there's the same correlation between X and Y. It happens to be an R of 0.816. So that's a pretty tight relationship. And then also the same equation for the linear regression, which is Y equals 0.5X plus 3. So we can see there are differences here in the numbers, but when we calculate the stats on the basis of those numbers, we get to 4 sets of data that seem like they're all the same, but they're not. And one of the best ways to find that out is to plot out the data. And when you plot out these data sets, this is what you get. These all look pretty dramatically different from each other, but all these stats based on these numbers are the same. So we're getting kind of 2 totally different views of what's going on in the data here. Maybe the most dramatically different one is this set number 4 here, where we have a whole bunch of points lined up at X equals 8, and then one where X equals 19, and then Y gets stretched out way over there. You can see they plotted the best fit line on all of these, so you can see that one is exactly the same, which kind of accounts for our last 2 stats there, or similarities there. But obviously these are different. So this is one where you have a bunch of, data points at the same X, and then one outlier here to the right. And this looks like you're kind of plotting a straight line here, but there's one outlier here, which gives you the same sort of stats in the end of the day. This one kind of looks parabolic, and this one looks sort of like a normal sort of scatter plot that you might run a regression analysis on, and you can kind of easily understand why the best fit line fits right there. The Wikipedia article on this, because I looked it up, says that nobody really knows how he came up with these sets. He just did, because he was interested in stats and like playing around with numbers like this. But my guess is that he probably had this set of data. What is this, like 10 different data points? And like he ran these stats. He's like, how could I get this in some other way? So it's like, how can I get this where there's all the X values are the same except for one? Or how can I get this where it looks like another line except there's one outlier, that sort of thing? Or this, it kind of looks like half of a parabola. Yeah, that's probably what he's doing, I guess. But either way, the point is always take a look at your data, because you don't have a sense of what's going on in it. Your sense of what's going on in your data is not complete until you do that, because all these numbers here are not going to tell you that set number 2 looks like kind of half of a parabola, or that this one has just one obvious outlier, that sort of thing. So that's Anscombe's quartet. Those are the 2 sides of the equation, the 2 sides of the process that we run. always do the quantification analysis or the quantitative analysis of your data. Always kind of do the intuitive part of it too to get the whole picture of what's going on. The last thing I'm going to mention in this part of the lecture is the R to Z transformation. And this can be useful. This is a question that has come up in this class many times before, including in that 2013 class. But if you want to determine whether two R values are significantly different from each other, there's a method you can use, and I picked this up from the Introduction to the Practice of Statistics textbook. And it seems like it works just fine, but I don't see it used that often in linguistics research, but you can because it's statistically valid. So what you do is that you can take the Z transformation of both R values, and then basically conduct a two-sample Z test on the difference between those R values. So the specific approach you have to use, this is from our friend Mr. Fisher again from back in the day, but if you have an R value for your set of data, you put it into this equation to convert it into a Z value. So the R value again is going to range from -1 to 1, and the Z value will be normally distributed. That's basically what you get out of this. And to do this, you have to use this natural log function, which is symbolized ln here. And you take the natural log of 1 plus R divided by 1 minus R. So I'm not going to walk you through what that means at this point in time. If you have taken my 341 class, we talk about logarithms a bit. We're going to talk about logarithms again later on in this class, but for now, don't worry about it. You just have to run the right command in R, and I'll show you how to do that. But basically what you get out of this is something that transforms the R value, which has limits on how big or small it can be, to something which is distributed normally, and we're calling that stat Z. The standard error for this statistic is 1 divided by the square root of n minus 3, or n being the number of items in your sample. But for if you're trying to compare two different values of R against each other, then you have to pool the standard error. So the way you do that is with an equation that looks like this, where you're basically adding 1 over n minus 3 for the two different groups within that square root function. Okay, so that's not super complicated, thankfully enough. And this is the only case I know of where we're subtracting 3 from n, and I don't know exactly why, but I'm not going to get into that now. We're just going to have to do the math without thinking about it too much. So I want to give this a shot with our snippets of familiarity and frequency data. So the first thing is that I'm going to sort out those theoretical QQ or quantile values for both distributions, and I'll call them fam QQ and freak QQ for whatever that's worth. And again, this is just for these familiarity and frequency numbers from the first 20 words in that database. And then what we need to do is calculate the R values for the two different calculations. Actually, I haven't looked at this. So these are just where the QQ values are supposed to be. And then if we convert those into R values, again, what we'd expect to get here is a value of 1 if these guys are normally distributed. They should all fit exactly on that QQ line. But what we're seeing here is R values that are slightly different from 1. So this is the one that's supposed to be normally distributed here, according to the Shapiro-Wilk test. This is the one that's not quite normally distributed, so it's a little bit lower in terms of its R value. And the question here is this R value significantly different from this R value? I mean, you can kind of think that maybe they are based on the results of that Shapiro-Wilk test, because one winds up being normal and the other does not. But we'll approach this using this R to Z transformation and see what it tells us. So to convert those R values into Z scores, this is what that equation looks like. So going back up here, this guy, if we do it in R, it'll look like this. So 0.5 times the log of all this stuff. And again, if you're concerned about this, it's referred to as the natural log here, log to the base e. When you use that function in R, you just say log, which if you learn math like I did, the default was base 10, but it's base e here, so don't worry about it. Either way, this is just the equation you use, 1 plus R on the top, and then 1 minus R on the bottom. If we just plop that all into this variable famz, we get a z-score of 2.35. Going back to the second half of that, we need to do the same thing for the frequency R value, like this, and we'd expect this one to be a little bit lower, right? Because our R value is lower, and in fact, we do get a z value of 1.7. This is kind of like we're taking two samples of R and trying to test if we can legitimately say that they both fall on the same sort of underlying population of R values from whatever data we're trying to correlate with each other. So the z-score means that our expectations are that sort of the underlying population of R values is normally distributed. At this point, we have a z-score of 2.35, so we're pretty far out on the right tail. And for this one, we have a z-score of 1.7, so we're not quite as far out on that tail. To sort of normalize what the probability is of getting those two measures from the same distribution, we have to figure out what the pooled standard error is. And to do that, we just use that equation that I showed you before. It winds up having a lot of parentheses in it, but this is what it looks like right there. And in this case, our n's are going to be the same in both cases because we just have 20 samples in both, right? So the 20 here is just referring to the data frame. This is not, the number. It just happens to have 20 lines in it, right? So in case there's any confusion there, hopefully that clears it up. But now what we do is we calculate that difference between the two means. So this is the two sample part of this z-test. We're looking at how different these two z-scores are from each other with respect to that standard error. And we get a difference of negative 1.9. Okay, so it's negative because I'm taking the smaller value and then subtracting from it the bigger value and going this direction. All I need to do next is just take the p-norm value of that RZ score. So I just want to convert this sort of test statistic result into a p-value. And in this case, I get a p-value of 0.02854278, so on and so forth. Yeah, so that looks good because it's lower than 0.05, right? So that seems to suggest that this is a significant result and that these R values are significantly different from each other because we're beating the criterion there. But you, or we, in a sense, got lucky here because we could have totally done this in the opposite direction. And in that case, I would have done the RZ score calculation this way by, instead of starting with frequency Z and subtracting fam Z, I'm starting with fam Z and then subtracting frequency Z because I didn't know ahead of time necessarily which one was which. And in this case, why did this happen? I don't know. Let's go back up to, I think it's just the translation from PowerPoint. Let's just go change the first one we used, which worked fine. And now we have an RZ score of that. And if we take the p-value of that RZ score, we get a p-value of 0.971, which is not significant. And the thing is that this is just showing us sort of the other tail, right? So we expect this thing to be normally distributed in terms of, the difference between the two R's. And if we look at the difference in one direction, it's going to put us way out on the tail on one side. If we look at the difference in the other direction, it's going to put us out on the tail on the other side. So we should run a two-sided test here. And for that reason, I'm going to suggest that you should kind of do it both ways if you're making this calculation. Whoops. And in fact, easier way to do it both ways might be to say, make this, sorry, I'll do it differently. I'll say this one is RZ score 1. And then I'll call this one RZ score 2 so that you can at least maintain both in your memory or your console for R. And you should take the one that's smaller, which in this case is this one. It's negative 1.9, or I guess another way to put it is more negative. And then you should double it. So take 2 times the p-norm of that RZ score, and that is the way you can run a two-sided test for this. R to Z transformation. So in this case, we are a little bit out of luck because that boosts us over the 0.05 criterion. We get a p-value of 0.057. So unfortunately, this is not actually significant, even though it seemed like for a bit there it might be. So that's the conclusion you can draw, and that's how you would run the two-sided z-test if you have to try to determine whether two R values are significantly different from each other. But these, which look pretty close, are not significantly different from each other. They're just sort of superficially different from each other. And I guess I'll mention that as well, as long as I'm going to wrap this up. But unfortunately, when you do get a non-significant result like this, you just accept the null hypothesis that they're both coming from the same underlying distribution. So even if you see sort of superficial differences like this in your data, whether it's mean values or R values or whatever, you kind of have to toss them aside and say, oh, you know, it looks on the surface like there's something going on, but there's not. You don't say at the end of the day, oh, the familiarity R is bigger, because your statistical test didn't show that. And if you do that, you're just going to get more sort of false alarms than you really want to anyways. Don't draw any conclusions from the results of a null test other than just like, I'll accept my null hypothesis. Don't draw any conclusions from the results, the non-significant results of a test other than I'm accepting my null hypothesis. I think I've spoken enough for now. I'm going to stop babbling over myself. Like I said, next time we will talk about analysis of variance. So we'll move on to something different, which is still based on what we've been talking about already. So I will look forward to seeing you all then.